Okay, so hey there guys. If you don't know me, my name is Premal. That's my boy Niraj over there. Or Captain Spark on some of the...
Commander Radon.
Commander Radon, that's it.
Hello, Captain Spark.
So today we're going to going over line integrals. So my aim kind of today is to try and give you lots of more sort of geometrical interpretation, a better physical understanding of, like how it can be applied to problems and things like that. And also, there's a bit of funny maths also, like in terms of definitions and stuff that I'll be going over. But so the first half is going to be a bit like what Sam just taught you, but then the second half is really going to be getting into the really interesting stuff. So let's start here. So you may have seen, so here I'm going to try and just make a comparison between line integrals and normal integrals. So under a normal integral, you have some function and you integrate it with respect to some dx. In this case, it's our x-axis. I mean, if you like. For every point on, you kind of, if you're familiar with the whole trapezium rule idea, it's the idea is that this integral is making lots and lots of little rectangles or trapeziums between here and here, and it works out, in this case, the area under the curve. So line integrals is quite similar to that, except the main difference is that instead of integrating against an x-axis, instead what you're going to integrate is over a kind of a line on the xy plane. So I mean, this line could be anything. It could be something weird like that, and you could literally integrate your function like that. But I'm going to try and stick with simpler ones. So this one's just a line. And so the bit that tells you what you're integrating over is this c here and this ds. If you like, c refers to some curve, and in this case it's just this line over there, and ds refers to kind of you see it's this here. And now, one thing to note with line integrals is, at least with this example, that you have this this function of xy. Now, this in this graphic over here, this f of xy is represented by this sort of red cone-shaped thing. One way of thinking what this f of xy is doing is, let's say we wanted to plot the temperature of this room at different points. So if we took, like, say, that as being the origin, you say that's our x-axis, that's our y-axis. And what I'm going to do is I'm going to kind of make an imaginary z-axis, the upwards. I'm going to say, okay, the temperature at this point is really, really hot, like 50 million degrees. And then if you say go for a different point, say, I don't know, somewhere around there, it may be, say, 50 degrees. And so you say, at that point, okay, the temperature is 50 degrees, at this point over here. But at this point, the temperature is 500 degrees, so it's a bit higher up. And so you kind of make this 3D kind of representation of your xy plane, and on your z plane you have the temperature. So that's kind of what we're doing over here. We have this xy plane over here, which in this figure, this is actually just the xy plane. This is x, and this is y. And then our z-axis, in this case, is represented by this function f of xy. So this f of xy actually depends on both. So this function actually depends on both the x and the y. Yeah. So, you can literally, the idea is that you can go to any point on the xy plane and it will give you a value, some value from this function. And so the idea of the line integral is that this ds, at least in this case, it refers to this line over here. And so in the 3D diagram, that line is this line over here. And so what you're integrating when you do a line integral is you're integrating, you're taking all the points between here and here, and you're making a little trapezium using your function, and you're kind of, it's almost like if you had a curtain over your function. You're drawing a curtain over here. What the line integral is doing is it's calculating the area of that curtain. And because this is in terms of, our function here is in terms of x and y, and we're integrating with respect to some ds, we've of course, they don't, it's like comparing apples and oranges. They don't necessarily mix, so we have to convert them. In this case, we're going to do into parametric, called parametric coordinates or something like that. And so we're going to make them both in terms of t, and then we're going to convert our ds into t using this little definition over here. This will probably make a bit more sense as I go through some of the examples, but like that's the kind of general gist of it. So two little notations you should note here. There's an open integral, an open line integral, and a closed line integral. So
Just to summarize what he said over there. So again, the whole purpose of using line integrals and not normal intervals is that in line intervals you have fields. So the first question that might come to your mind is like, why do we use line intervals? Why not just normal integration? Why do we need all this extra stuff? The extra stuff is because that is used to integrate fields. And what that red cone and temperature example meant was that. Before that, let's just have a quick look at the concept of fields. So field is if you give a value to every position, every point in space. Say you give me a coordinate, say x and y, and I return you a field like a value, say 10 or minus 20 or square root of 17. And I assign these values to every point in space. So every value of x and y has a value that I keep in my little log record. So what happens is there is no z direction by itself. It's just x and y really. But what we do is we say, well, it's sort of difficult to talk about. Well, there's really three values over here. There's the coordinates x and y, and then there is this new value that is assigned to each of these points. So there's actually three values that that really kind of express and define that sort of shape. And so all we do is we say, well, we can encode this information by introducing this new axis, essentially z-axis. So this pictorially represents what's really going on. So if you see a temperature field, as you said, and you see 100 degrees over there and 20 degrees over there, it's sort of like, if you see it in a 2D plane, you might show it with colours. You'd probably show red over there and yellow over here, and blue over there. Sort of a bit difficult to understand. Or otherwise, what you could do is you can just assign heights. That say 100 is 100 meters, 100 centimeters, or 20 is 20 centimeters, and minus 10 is minus 10 centimeters. So when you do that, it becomes more pictorial, it becomes more graphical. We can imagine and think, oh right, so there's sort of a difference in temperature. That is the difference. So you sort of encode that information pictorially. And this is the whole concept. That is why we use line intervals. So the whole point of line intervals is that you have a field. You don't just have two x and y values, but you have a third value that is assigned to each of those values of position. And they sort of they sort of ask you about that field. I mean, something like, what if I go through, say, that point to that point? How much temperature change will I feel, or something like that? Another point I'd like to make is that you must understand one thing very clearly. The reason, let's start with something else. Say this is the origin, right? And I say, what's my distance to that point? And what I do is I would take the x and the y, and I would sort of do x squared plus y squared square root of the whole thing, and I'd give the distance. My point being that the distance function over here is actually depending on the point I choose and pick, right? But temperature is not like that. The source of the change in temperature is something else. It might be there's a radiator over there. That's why it's hotter than this point. But you still need a position. I mean, it depends on the position, but implicitly, it doesn't explicitly depend on the temperature, in the sense that choosing your point does not change the temperature. There is another source of temperature which produces the whole change, but you sort of map each position to that value. So what I mean by that, or what I mean by all of that, is that if you have a distance function wherein the function itself depends on the values of x and y, you do normal integration. All you need to do is just, that there would be something like f of x is x cubed, so it actually essentially depends on x. You plug it back into the equation and you get x cubed dx, you can solve it. But over there, it's not like that. It's like work function, for example. You have how much work is being done if I or else temperature. How much temperature change do I measure when I go from one point of space to another point of space? So what I do is I take these little steps. I take, first I see my path really. For example, I want to go to primwise. I want to go straight because that's not interesting. So what I'm going to do is I'm going to take a wavy part of it. What I do is I take I have a thermometer in my phone app. And I take a small step, so I can actually go all the way, but it records temperature every 1 millisecond, 1 second. So I have to wait after every second, record the temperature, and go and so on and so forth. So what I'm going to do is I'm going to take these little steps, really. I'm going to see, okay, my path is like that, so I'm going to just take one little step, wait for the temperature to update, record it, so on and so forth. And at the end I get these values in temperature changes, I add them up, and that is essentially the net temperature change that I undergo if I took that path. Now, why is this important? It is important because it might be the case that sometimes, there are physically, there are two functions really. One is called the state function, and one is called the path function. State function really just depends on the positions of the state, my initial state and my final state. So it doesn't depend on the path I've taken, something like gravitational potential energy, for example. You're here, then you go here, like straight down. The change in gravitational potential energy is just the change in the height times the mass times the times g. Say I take a more sort of path like that, it still remains the same. It's still mg delta h. So it's a state function. It just depends on the initial and final states. But work, for example, like friction, work due to friction, it actually depends on the path taken. If it's a smaller path, the work due to friction is quite small. But if it's a sort of, you just move like that, then you've got a longer path, so the work due to friction changes, it increases. So that's called the path function because it depends on the path you've taken. Line interval is something is useful for path functions, wherein it really depends on what sort of path you're taking to reach the initial and final, to reach the final state from the initial state. So the final point is line intervals are for fields to something that do not essentially depend on just the position. They have a randomized value at every coordinate, and we need to find something about such a field. So remember, line integrals, when you do line integrals, you're doing essentially vector algebra, or you're talking about fields. Yeah.
Sweet.
Alright.
So don't worry, a lot of that where we're going to be going over, we're actually going to go over a couple of physical examples later on, so some of that didn't make sense, we should probably click on that as we go along. So two things to define here: open line integrals and closed line integrals. So so this integral here is an example of an open one. If you like it, it just sort of goes, it kind of like takes a walk, if you like, from this point to this point. And actually this couldn't look in any this closed, so this open and integral, path integral, can actually look anything. It could be some weird squiggly line. I just chose a straight line because it's simple. And the other example is a closed line integral. So they tend to be with the funny notation, with that little circle thing over there. And so a closed line integral is an example of a closed integral. A line integral would be a circle. So when we had our xy plane, instead of drawing a line, if I say drew a circle, something that kind of if you like, touches itself. That's an example of a closed line integral because it's a closed loop. Okay, so now I'm going to go over an example. This time I'm going to go over a closed loop integral. So if you remember, we had the definition over here. And so we're integrating this function x plus 2y dl, where our c, where our curve that we're trying to integrate over, is defined by this little triangle here. Like just by this point, and this point. And so the way that we're going to work that out is actually we're going to split this integral here into 3 parts. We're going to split it into the part that goes from here, from O to A. Then the second part is going to be from our A to our B, and our third part is going to be from our B back to our origin. So to do that, because these are x and our y's, these are our integrals in terms of x and y, we want them all to be the same variable, so we're going to do a couple of little transformations. So for our first one, our x is equal to t because you see it just increases linearly, and our y is constant here. From here to here, you can see here that both our x and our y change, so I made x equal to t and y equal to 1 minus t, which is that line there. And for our third part, we're going to say that our x is constant, it's fixed, it's 0, and our y obviously changes. And so yeah, so now I'm going to take the first side from O to A. We put our little substitutions in, these ones into here, and then we integrate. We know that our t is between 0 and 1. We defined that when we're making our these changes or whatever you call them. And yeah, so you just integrate like that, and you get 0.5 for the first one. And if you take the second example, the C2 from A to O, you then just substitute these things into the equation, and you also substitute. One thing I forgot to mention. If you see here, where did it go? Okay, so if you to convert between dl and dt, we have to use this little definition that we had over here. And so if you take the derivative of this, you just get 1, and you take the derivative of dy with respect to t, well, that's just 0. So that in this case, our dl is actually equal to our dt for c1, and I think for c2, this factor of root 2 comes in from that little differentiation thing, where you differentiate x with respect to t, and you get 1. You differentiate y with respect to t, and you get -1, and that gives you a little factor of root 2 there. You put on the outside, and you make your normal substitutions like we did the last one, solve it through, integrate, and you get that. We'll do the third example, the third point from here to here, in the exact same way. And now that we said here that our entire integral is equal to all these different parts added together. So you just add up all the parts that we got from the previous part, from the previous slide, and yeah, you get some number like that. So I'll just quickly show you now what that kind of looks like on a graph. So you remember here we had a triangle on our xy plane, and our function was x plus 2y. So this will be represented by our z-axis. So here's what it looks like. So this red plane here is actually our x plus 2y, and we have a little. I know this is not the best triangle. Unfortunately, the program doesn't like straight lines; it only likes curvy lines. So I have to make it slightly curvy. But so this is the triangle that we had. And it's represented if I rotate that around. If you see, that triangle is that triangle. And then when you integrate, when you do the lineage code, what you're actually working out is the area of that kind of curtain that comes from our triangle up to directly above to our function x plus 2y. So that's what the area that we worked out there. Okay, go through another example. This one's going to be slightly different. This is going to be an open loop integral one. We're only going to do half of a circle, and so so our circles normally in Cartesian coordinates are defined by this little equation here, but in parametric coordinates they're defined like this. So because we need to differentiate it anyways, we're just going to differentiate them now. And you get those two, and then like we did beforehand, we're just going to substitute them in. In this case, I'm going to use limits of -π/2 to π/2 because I feel like this is kind of it's a polar coordinate system. So you feel like you're integrating that. If you imagine like that's you're starting from -π/2, you're integrating to π/2, so you're integrating sort of an angle of pi, and that gives you half of the circle. You work it the same way, get it, and you get some big number like that. I'll show you that one on the graph. Got to put it on my phone up there. Okay, so this is imagine this is a circle. Unfortunately, it doesn't like circles either. So, if you look from the top-down view, that's the circle that we have here. And if I put that to standard view, this red thing is what was defined as our x plus xy to the power of 4. And the same way, you're going to calculate the area of this little curtain over here. Okay. And hopefully that should pick up.
The best way to do it is n is just y2 minus y1 step minus 3. So y2 minus y1 is minus 2 minus 3 divided by x2 minus x1, so 5 minus 1, x plus c is equal to y. Don't know c, so okay, I'm just going to solve that over here. So minus 2 minus 1 becomes minus 5, and 5 minus 1 becomes 4. Right, then all you do is you just substitute some point over that. Let's do the first one because it's easier. And that makes this 3 is equal to minus 4 over 4 times 1 plus c. You get c from that, because this is just that, and this makes c 3 plus 5 over 4, which is just 17. Right. So you just plug this back over here. This is the equation of the path that you're taking, so you get 17 over 4 over here, and we get all this. Alright, now you have the path you're taking. Essentially, this is the curve that you're traveling through. But the function that you need to integrate, the z kind of component is that, and well, okay. Now the point comes why we need to parameterize the whole thing. Here, experience helps. When there's a circular path, for example, if you do too many problems based on that kind of situation, you probably see that r cos t, x is r cos t, and y is r sin t. It's easy because you need to like ds includes So ds includes dx dt and dy dt. So you want something that's really easy to differentiate. So say you have some part like x squared plus y squared is some r squared. And there are millions of ways you can parameterize that, but this is one of the way, and it's quite simple because the differential cos t is minus sin t, and sin is cos t, so it kind of makes it really simple to do. But there's another way, and okay. The general way to do this is for taking x is equal to t and finding the subsequent y value by just putting t in place of x. Over here, it's going to be t squared plus y squared is r squared, so y squared is r squared minus t squared, and y is square root of r squared minus t squared. Now my point might be clear over here, as you can see that differentiating that might be a bit of a hassle. So if I compare to that, so experience helps solve more problems, find better solutions to solve it. Otherwise, just use the most general sort of parameterizing technique, that is take x to be t and your subsequent y from the path. Over here, it's going to be over here, it's going to be x is t, y is minus 5 over 4 t plus 17 over 4. All right, step 2. Now, if you've thought of parametric equations, we have our normal curve to integrate. So what we do is we transform this into the corresponding parametric form. X is t, so I'm just going to put t in place of x. Y is that, so minus 5 over 4 t plus 17 over 4. There's a ds over here, and wrote it earlier. Let's use this. Right. So ds was square root of the x squared, that, dy dt, that, now, you know x is just t, so if x is just t, differentiate that with respect to t on both sides, you're going to get dt, which is just 1. So you know the x. I'm going to skip this step and just write as 1. So you know that. Similarly, write y minus 4 t is 17 over 4. Differentiate that both sides with respect to t. You're going to get t dy dt is equal to constant, jumps out, minus 5 over 4 dt dt plus a constant. Differentiating the constant gives you 0, so it's 0. Don't add zeros. That's a 1. So dy dt is that. So ds essentially becomes ds is dx dt. So dx dt is 1, so that's just 1 squared. And the 1 dy dt is minus 5 over 4, which becomes square. I mean, when squaring it becomes 25 over 16. Sorry, I think I told you it was a 16. There you go. And there's a square root. And there's a dt. Now that becomes 26, 49, 7 over 4 actually. Right. We have ds as well, so now we're going to plug ds value there, and we're going to get 7 over 4 dt. Right.
41 is not this 7.
Good. Sorry.
Yeah, it's
Bad job, guys. Just 1 point. Got a point now.
10 points.
Anyway, right, that is 41, and now you just have to differentiate this or integrate this. It's not going to be that difficult because it's just a constant. Just no, it's just more fun. Anyways, this is square root of t minus, going to open the bracket, plus 5 over 4t times that. Multiply that. 5 square root of 41 divided by 16t minus 17 square root of 1 divided by 16. And that is dt equals 4. That's well, this plain equation sorting thing. This is just a constant, it just comes out, it becomes integral of t dt, which is t squared over 2. That is just a constant, so it just gives it t. Right, but we're not done yet because we have an initial point, ti, tf. Ti is 1, t initial. Since x is ti, x what I is 1, so ti is 1 as well. Xf is 5, but we know xf is tf, so tf is 5, and just plug the limits over here from what's that? 1 to 5. Put it back in, you're going to get 25, yeah, just sort of. Right. Any questions?
As does though, if it's minus 1.
See how you put Is t like the imaginary
Oh
yeah. It was actually like the value.
No, what you're trying to do is you're trying to bring both x and y into the same variable. So if you give the value of t, you're essentially giving values of the x and y. So it's not the z value. The z, this is the z.
The one outside the bracket.
Oh, you do.
Good catch. Sorry. Right, it's supposed to be the So yeah, now it's not going to give you the right answer. That's how you do it.
You want to have fun?
I wish there was an easier way.
Well, maths.
Okay, no worries. We'll move on with the lecture, and then I think for the next set of problems, I'll give you the parameterized thingamabobs, and it'll make it a little bit easier. But anyway, has everyone got that down? Anyone says it?
No, I swear the lecture was 100% video.
It's another point. So we're trying to complement the lecture notes, but not exactly go through lectures again.
So he does it in a way where there's no parameterization.
Yeah,
Anyways, I think it's sort of better to use
It
parameterization.
sort of makes more sense with the maths.
Because
So I already know.
Last year there was a question that I think messed screwed everyone's results, and that is parameterization. So it's good to
For fuck's sake.
Record down.
I want 0.
Can I
Okay, no worries. We'll carry on with the lecture. Please not. Oh, you're asking a question.
Please not raise your hand. No question. I need some.
right.
Okay, so yeah, carry on. We're gonna go through now a physics example, like an application, like of line integrals. So next problems I'll give you parameterization, so don't worry about that. So if we take this example, f.dr. So I mean, you may be used to the idea of work done. You may have said, I don't know, in A levels that work done is equal to force times by the distance moved in the direction of force. We're in uni. The issue with that is you can only apply it for straight lines. But with line integrals, we can do it for funny shapes if you wanted to work out the work done against friction for like a squiggly line or something like that. So we're going to rewrite this a little bit. And we're going to say that dW is equal to the force, we'll say it's constant, times by dr. These are vector things. Yeah. So like force, the work done is equal to force times by the direction by some infinitesimal small unit of length in the direction of it. So if we integrate these both on both sides. Now the thing is, we're going to have to use line integrals for this because this is in terms of r. If it was in terms of x or y or something like that, it might work, but because it's in terms of r, because they're both vectors, we're going to use line integrals, and I'll show you that in there. Slides. Okay, so in this case, our force is equal to this. Is everyone familiar with this form? You know, if I put an I, J, and K, we've probably done it in fields and waves or something like that. So this is the component of force. It's in the I direction, J direction, and K direction. So we're going to try and work out f.dr, where our r is that. Now, to work this out, firstly we're going to need to substitute our r into our force equation, because obviously it's in the direction of r. And then we're also going to have to figure out some way to get rid of that dr. And so the way I'm going to do it is I'm going to make this funny little. It's similar to parameterization. The only it follows from chain rule, but you're going to say that timesing everything by the derivative of dr over dx. So the derivative of this with respect to some x. Oh, sorry, I should be teaching you. I don't know, whatever. It's going such a funny place.
That should be T.
Should be T, yeah. Okay, ignore that, that's T. So when you substitute
D or DT?
dr by dt and dt.
okay.
Should I change that right now? I can't right now. I'll change it afterwards. So you substitute the force in and you get something like that. And this is weird. Okay, yeah, so substitute in the force, and then because we wrote here that the force times by the dot product, we have to dot it with our derivative of r. I worked out the derivative of r here, by the way. That's the derivative of this with respect to t. And now our formula tells us that we need to dot the two. So we're going to dot the two, and we're going to get that equation, and then integrate between 0 and 1, because that's what our parameterization thing told us. And then yeah, we just do it how you normally solve integrals. Here are some problems. I wrote down here the parameterization for for the r. So this is your x, this is your y, and this is your z. I, j, and k. Yeah, have fun.
Yeah. As a physics problem, you can prove that. Well, you can take the gravitational potential and prove that it is not a path function. That it doesn't depend on the path. Just take the same initial fun points, take two different parts, and you'd see that it still gives you the same integral. Say friction. Yeah. Just if you're interested.
Yeah.